Good afternoon, everyone. We're going to spend the afternoon talking a little bit about what engineering actually is and what physical science is and how the two interact. And then just sharing a lot of ideas that I hope you will be able to bring into your classroom, no matter what kind of situation you are teaching in. I've had experience as an early childhood special education teacher, as a professional development person in the world of childcare. I've done collaboration with Head Start and was a college professor and co-author of a number of children's books in early childhood science. And then had a National Science Foundation grant with a couple of people and worked in Texas with preschool teachers down there for 4 years, looking at what children know and can do in science. And so what that has done for me is helped me figure out ways to help teachers and children benefit from science and engineering in ways that promote not just science and engineering, but overall positive child development. So we're going to talk briefly about this idea of STEAM that and there are a lot of variations on it now. But I think it's important to realize that when we use a term like STEAM or the different variations of STEM or STREAM or other things that incorporate other disciplines, is that it really is what the world of early childhood is all about. And that is that interdisciplinary kind of thing that we rarely do things that are one topic only. If we're doing art experiences with children, we're doing language development as a part of that process. When we're doing mathematics experiences with children, we're also incorporating fine motor. That's just kind of how we work in the world of early childhood. It also really connects with whether you're doing project work, interdisciplinary studies, creative curriculum investigations. All of those come at learning from multiple perspectives and content areas. And so that's just kind of my way of working with children, whether they're children with typical developmental profiles or children with special needs of one kind or another. So you might wonder, why this matters so much at the preschool level. And one of the things that we've discovered is that STEM, or various aspects of science, technology, engineering, and mathematics are part of the future of our world. And so right now, I think the current numbers are roughly 24–25% of people in the workforce are doing jobs that are somehow related to STEM. That includes people with college degrees in those fields, but also people with other learning backgrounds in those areas. We're anticipating at least a 10% increase over the next 8 to 10 years. And so it matters. What we're looking at now is that 65% of the children will work at jobs that don't exist today. And so part of our job as early educators is to help them learn how to learn and learn how to think. I'm not going to read all of these bullets on this slide, but it is apparent that science, technology, engineering, mathematics, the arts all work together to encourage thinking in complex ways that will support whatever kinds of jobs emerge when these little children are entering the workforce. The other thing to bear in mind is that there have been a fair number of studies over the last probably at least 8 years that show that children who enter kindergarten with limited math and science backgrounds and skills are just as unlikely to catch up in kindergarten and beyond as children who enter kindergarten with low, limited language and literacy development and experiences. And so it's something that really matters and that we can do things to make a difference in. So one of the things that we want to do is think about math and science programs, STEM programs, not only focus on that content of science and math or engineering, but they focus on the behavior traits. And we'll be talking about this quite a bit over the next hour and a half. Things like perseverance and problem solving and patience and struggling with something, experiencing something that doesn't work, experiencing that sense of failure. We tried that and it didn't work. But the understanding that that's part of the process. And helping the children with self-regulation to manage the challenges and frustrations and stick with it. So let's talk just briefly about the differences between science and engineering. Science focuses, and these are very simplified definitions, but the basic idea is that science is about finding information, systematically studying the physical and natural world through observation, experiments. So let's take just a moment. Here these kids are using these fancy observational tools to focus their observations. Take a moment and try it yourself and just take your hands and make a tube and kind of look around wherever you are and see how it changes your perspective. It's surprisingly effective in eliminating visual clutter and helping you notice more details. So do it once again, just kind of look at something and see how when you look at something through that narrowed field of vision, you see things in an entirely different way. And that's what we're trying to do when we help children look at the world. Engineering is about solving problems and designing solutions. So we can support engineering skills by pointing out opportunities to use them. So in this image, we have a frustrated group of children. They're talking about it keeps bouncing out of the bottom ramp. So they're trying to roll balls from this ramp, get it to land in the bottom ramp and continue down. It keeps bouncing out of the bottom gutter. So if you're going to be a teacher, an adult, or whatever your role is in promoting engineering, you might say, oh, what's the problem? It keeps bouncing out. That's what the problem is. Well, let's think of some ideas to try and generate some ideas. Okay, let's try some and see if any of our ideas work. And if they don't work, we'll think again. You've just promoted engineering. It's probably familiar to you from your childhood. I would be willing to bet that most of you attending this webinar right now at some time in your childhood built a fort, built a tent out of couch cushions and blankets, made a hideout, built little things for dolls or animals or cars. That's you as a child defining a goal of what you want to make, you know, building a hideout that's big enough for you and your friend or your sibling or whoever, doing something that's going to be the right size to fit whatever toys you're building it for. That's you solving a problem through trying ideas and seeing what works. So one of the things that we're talking about with children in our world today is that we want children to feel competent and capable. But competent and capable teachers are just as important. So what I'd like for you to do right now is take just a minute and in the chat, write on a scale of 1 to 4, how competent you feel about teaching physical science. Most early childhood teachers are pretty comfortable with the nature-y stuff. On a scale of 1 to 4, how comfortable are you teaching physical science? And just put it in the chat quickly. So it looks like we've got 2 to 4s, 2 to 3s. So most of you are in kind of the medium to competent range, some feeling a little bit more confident than others. So now let's take a minute and look at this learning standard. Explore the concepts of force and motion. That's one of the Illinois Early Learning Standards. Here's the benchmark. Explore the effects of force on objects in and outside the early childhood environment. And here we have a performance descriptor, which is just sort of an example of what this looks like in practice. So explore the impact of their own use of force and motion on objects. So here are these little guys. This is part of my Texas group. They have a collection of salad dressing bottles, detergent bottles, other kinds of squirt bottles, and they're filled with water, and they're seeing which ones squirt the farthest. And so now when you think about, and we're not going to do another poll, but when you think about this activity, I think most of you, oh yeah, I could do that. And that would be kind of a cool thing. And I could talk to the kids about it, and we could sort those bottles. Once we've done the squirts, we could maybe graph, we could do a bunch of different kinds of things with that. And I would bet those of you that were in the 2 range, thinking about how you can do teaching physical science, maybe feel a little bit more confident that maybe it's a little bit more simple than you thought. So now, would you do the same thing? Put in the chat how confident and capable you feel about teaching engineering. Get on 1 to 4. So it looks like, you know, our confidence levels are a little bit lower, which really isn't surprising. I would be willing to bet that we've got one who says, I love pull and push and ramps, and I'm going to share some stuff that'll be right up your alley. But most of us did not learn about engineering in our own school experience. Most of us did not have any experience with an engineering textbooks. Most of us had a science textbook at some point in our school career, probably at several points in our school career. And so engineering is a little less familiar to us. But let's look at this. You know, one of our standards is developing beginning skills in the use of science and engineering practices such as solving problems. So here we have, in this case, a group of children who were involved in engineering a solution to the problem of getting balls and water down the hill in a way that was fun for everybody. So they identified a problem, they designed a solution, and they had to be willing to fail along the way. So look at this little girl, look at the muscles in her arms and how hard she's working. And I'm hoping this makes you feel a little bit more confident and capable with the idea of engineering. You know, I think most of you see this as something you could potentially do depending on where your setting is. So what we're going to do next is an in-depth look at science and engineering in practice, including how it addresses the Illinois Early Learning and Development Standards. And a science center is a good place to start. So this is, I think, a fairly typical early childhood classroom of a friend of mine. She decided she wanted to expand what she had as a kind of a little tiny science area, science center, to redesign her space to create more room for science. But then she took it a step further. She was an early childhood special ed teacher at the time. And she decided that she really wanted to work to create a more calm and serene place using more neutral colors to just kind of tone everything down a little bit with the hope that it would help. She had a number of children who were really had difficulties with self-regulation and things like that, and was hoping that making the classroom a more calm space might have a positive impact. And so those are the same cabinets that were here, but she covered them with really inexpensive muslin fabric. She brought in some plants, an aquarium, and just made it a much more calm space. And you can sense this feeling of calm and focused attention in this little guy sitting here or standing there in the science and discovery area. Just as an aside, this teacher worked on this similar kind of thing throughout her entire classroom over the summer to declutter, to bring in more neutral colors, to create a calmer space. And she texted me the end of the first day of school that she was amazed she had so many people stop by her classroom that day and asking how many kids had gone on meds over the summer because the kids were so much more calm. And she said part of it is the kids were more calm, but she said all the adults in the classroom were more calm too. We were doing it for the kids, but it really helped us. So just food for thought. So here's another strategy that we have science and engineering journals. Each child has their own box, literally a cereal box that's been cut to hold their journals. But what this does is it documents what they're doing and signifies to the children and to their families and to other adults in the school that it's an obvious interdisciplinary connection. They're doing language and literacy in conjunction with science and engineering. But it also tells people this work is important. It's worth paying attention to. So how we store materials matters too. I can remember as a classroom teacher, especially in the fall, the kids would always bring in colored leaves and sticks and things that they were finding. And it just felt like there were leaf crumbles everywhere. Having a little container for each child that they're in charge of changes all that. The children can decide what they want to keep, what they want to get rid of when it gets too full. The other thing, when you look at those materials, think about those materials as potentially building or collage materials and what else the children might do with them. Here's another science center. It's interesting, lots of interesting things, but it's kind of all mixed up and no focus. And there's no room for the children to work. The children would have a hard time kind of sorting out what they were expected to do. And I'm picturing those seeds that are on that little tray being on the floor in no time. There's something about light and shadow over here, but there's nothing that really indicates what they're going to do with it. So having some focus in mind and some effective storage can make a real difference. Bringing just a few materials at a time. So this teacher set out some gourds and some rocks, and the children had little round placemats they could build on. Rocks and round gourds offer a different challenge for building than with blocks. And it's an interesting sensory experience for them. Here's another classroom's science area. The materials are inviting. They're easy to either work on the table and chairs that are over here or on the floor. It invites more focused investigation and room to work. Here's another classroom. And I especially like her use of trays. So here she's got a water activity and a tray that's going to mostly contain that mess, hopefully. And it's science, but it's also a little bit of engineering thing. What's the best tool for getting water into a small bottle? Again, children can take things from this area to a nearby table or to the carpet. It's also interesting to take science into the rest of the classroom. So this teacher turned the dramatic play area into a geology lab, just like you might turn it into a pizza parlor or a grocery store to bring social studies into that area. I do want to talk a little bit about the use of props and stereotypes. We have the stereotype as the scientist, wonky hair, goggles, white coat, and that's fun to play with, but and play in science lab like that. But we also need to give children opportunities to see that scientists use tools, but they don't always wear lab coats. So you can be a scientist when you go outside to collect more rocks to bring into the geology lab, and you're not wearing lab coats and you're not wearing goggles. So they kind of see it both ways. But it does give science a bigger space for a period of time. So here they had a kind of a cool thing. They had a grandfather who had a fossil collection, and he brought fossils in for them to look at. I want to talk just a little bit about microscopes. Digital microscopes, and these, I will say, the microscopes that are in this picture, we used with teachers the first year of the grant, and even though they were supposed to be appropriate for preschool children, they really weren't. They were just ended up being kind of more play props than anything. What we ended up using a lot was a digital microscope called Zoomy that will actually, you can slide it over the objects and then it shows up on a screen like an iPad or a computer. It doesn't count as screen time for Eckers if you're using it that way, because it's just a way to view what's through the digital microscope. I checked that out with the state Eckers people. The Zooming one costs about 50 to 60 bucks, depending on where you get it. And it's sturdy enough that the Missouri Botanical Gardens over in St. Louis uses it in their children's center, and they've held up really well. So that might be something that you would want to look into. Then also the use of magnifying glasses. So a range of magnifiers is helpful. And even if the children don't yet have the ability to actually use them, and many very young children, typically 3s, don't. But what it does, they can hold it up to their eye and then they take it away to actually look at something, but it reminds them to look carefully and to pay attention and focus on what they're seeing. So what was interesting, a fun little side, I was in the classroom when they were doing this and walked over to look at what they're doing. And one little girl said, "Don't bother us, we're being dentists." Had clearly misunderstood dentists and scientists, but you get the idea. That's kind of the fun of teaching young children. So then again, across the other areas, we've got beyond the Science Center, sand and water table. So here, what's the best tool to move water for you? And it might not be the best tool for your friend to move water. Counting how many pumps of water it takes to sink a boat. And they're using a hand soap pump and this big pump. And what happens? How are they the same? How are they different? How many pumps or spoons does it take to fill the bottle? In the block area, what can you build using all the hollow blocks? They had a great time with this. What do you need to do to keep your tower from falling down in the block area? All of that is part of engineering. So if we look at one of our major science goals, this is kind of what covers most of what we're doing with this age group. Help them explore, become scientists, not consumers of science knowledge. So we want them to learn how to observe, to take a quiet moment, to listen to the sounds, to notice the colors that they see around them, to watch an insect passing by, and to celebrate attempts, even those that don't work. Maybe make a list of good tries, because engineers are people who solve problems, not people who wait for other people to solve problems. And so helping them understand that we make these tries, and maybe they'll work and maybe they won't. And if they don't work, then we just try another time. So here they're developing the beginning skills of science and engineering practices when they solve the problem of a ramp that keeps falling down. Children typically go through attempts time after time after time in rapid progression and don't really think about that process. And that's where teacher talk can really be a helpful kind of thing. So you can help them by kind of narrating what you see them doing. So you might say something like, I saw you try 3 blocks. You tried the square when it fell down. You tried the cylinder and it fell down. Finally, you found the rectangle that made your ramp stay up. You found a way to solve your problem. It's helpful for the builder, but it's also helpful for the other children who are nearby and listening to what you say. And talking about, you were determined, you were persistent, you tried again and again. So now you're going to get your chance. I think you were asked to put together a collection of objects to bring to this webinar and to make yourself a fancy ramp. You can use a book or a board, something to prop things up. I had a piece of cardboard. I don't remember what I put underneath in that picture. But make yourself a ramp and get out your collection of objects. I'm looking in messages as you're doing that. These classes, most of the pictures that I'm showing you are in classes of 3- and 4-year-old children. There are a few classes that are just 4-year-olds, and I'll let you know when those are, when that's the case, if it's relevant. So what I want you to do with your collection of objects and your ramp is to use your ramp as a tool to help you group them. And then I want you to write in the chat, what were the categories? Oh, and I want to be clear, none of the pictures from this presentation are from kindergarten. They're all preschool classrooms. Okay, you're going to take your ramp, take your collection of objects, and group your objects using the ramp as a tool to help you group them. And write your comments, write what your groups are in the chat. And we've got flat, round, and tall, things that slide, things that roll. Oh, flat, round, and ball, yeah. Shapes, magnetic, flat, circular. Wood items, balls of different sizes, so how fast they go down the ramp. That's how you use the ramp to determine how fast they go. Round and square small containers. Round, flat, metal, plastic. cylinder, flat, bumpy, wood, plastic, metal, flat, round, cubed, which roll, which don't. Okay, heavy doesn't move versus light, slides, roll and do not roll, fast and slow, slide, not slide. All right, you're going to take all of your objects, put them back in one pile. You're again going to use your ramp to help you group them in a different way. And again, type your findings in the chat. Nature objects, soft, hard, heavy, light, small, medium, large, heavy, light, squares, rectangles, triangles, plastic, wood, noise, no noise, colors, materials, foam, wood, plastic, glass, color, no color, pointy, flexible, things that are tools, those that are not, fast, slow, did not move. Okay, now I'm going to give you a different task. So if we look at, again, another benchmark here, expresses wonder and curiosity about the world by asking questions, solving problems, and designing things. You're going to take one object that doesn't move down the ramp and find a way to get it to move. You can combine objects using different techniques to solve the problem, to change how something moves. This is basic engineering. And again, once you figure out what you're doing, and then do a little description in the chat. So you gave it a push that made something that didn't move, move. Pushed it with hands. You can also combine objects. Roll it, put it the slide at a different angle. Put a marker under a play button and made it move down the ramp. Change the slope. Used other objects, put a cloth pin, a clothespin to move the object. Use one object to move another object. Used a rolling object to make it slide. So here's, your class would just throw them down the ramp. Sometimes they would, but you build up to this kind of thing. Put a sliding object behind it, use cars to move it down. Change the way I put it on the ramp. Oh, use a straw and blow air using my breath. So I used a bear, put a bear in the lid of a bottle cap, or in a bottle cap, and a bear on a sled slid down the ramp. So one of the things I want you to do is kind of look through the chat. Did you notice your vocabulary? You've been using nouns, verbs, spatial relationships, words like that. And if you were doing with this with children, you would be doing even more kinds of words with them. It gives a lot of opportunity for rich language. And I do want to just make kind of a side comment. As we go on, I'm going to show you some things that will, I think, work with children who are at different developmental levels. And again, you have to know your children as to how many objects you would put out at one time. Maybe you just put out two things. Maybe you just start out with one. Other groups of children can handle multiple objects. You have to know what's going to work with the children that you teach. So basically, you just did engineering. You identified a problem, something that wasn't going down the ramp, how to get it to go down the ramp. You thought of a solution, whether it was blowing on it, manipulating it somehow, pushing it, changing the angle of the ramp. You tested it, but then what's important is that you shared it. And there's a big piece that's often missing in the world of science and engineering in not just early childhood classrooms, but in elementary classrooms as well. And that is part of that process is sharing your results, talking about what you did and what you found out. And this is something that is excellent in supporting children's language and literacy development, obviously, but it also brings a sense of completion to an activity that you're doing. So this is from a classroom that was just 4-year-olds. This teacher regularly put something like this out in her classroom so that the children knew to look for something to try. So if you, I just want you to think how we phrase something matters. So this is a question that limits the answers to 2 groups. So if I had asked you when you were putting down the ramps, if I just said which ones roll and which ones slide, that's a good question. But I felt that you, as early childhood educators, were probably able to think in more complex ways than that. Again, you're going to know your children. Some children need that really direct thing of which object will roll down the ramp and just sort it into ones that roll and ones that don't. Other children are ready, perhaps later in the year, to be more open-ended about what happens when you put the object at the top of the ramp. It invites more discussion. What happens if we change the angle? What if we change the position of the object? You know, a cube will roll under the right circumstances. With the ramp at this level, it will slide or not move at all. If you tip the ramp up at a much higher angle, it'll roll. Think about rolling dice. It's a cube that rolls. Again, you know your children and what is the appropriate level of challenge for them. Okay. So now we're going to take a look at just miss something. Looking at the effect of force and motion. So if we look at, here's an example of a performance descriptor of, these are resources of ideas of what a benchmark looks like in action. So we're going to look at materials for exploring force and motion and how objects move. And I love this picture because of all of the repurposed materials that are in there. So right here is a piece of corrugated fiberglass that's often used for roofs of sheds. It's been just cut in a small piece and leaned against the chalk rail. Here's packing material that they pulled out of the recycle bin because the balls kept rolling all over the place and they needed something to corral the balls so they didn't keep rolling out of the block area. These pieces right here, there's one back here too, are packing corner protectors that come on, like when you get a new bookshelf for your classroom or a file cabinet or something like that, that is on the edge for packing. It's very stiff, sturdy cardboard that's at an angle. Little scraps of PVC pipe. These are Kleenex boxes that are covered in white paper. I don't know that I would bother, but this teacher did. These wooden pieces are what's called cove molding. It's molding that's used around the top of a ceiling. It comes in long strips, 4-foot lengths. You can get it like at Home Depot or Lowe's or Rural King or a place like that for about $30 for several pieces of it, and they'll cut it free in different lengths. But this is giving them a whole array of materials to try out experimentation with ramps and pathways and rolling. Here's a commercial version of the product. It comes from a company called Kodo, K-O-D-O Kids. A set, pretty much this a little bit more is $170. And then this is a piece of PVC pipe to roll the materials through. But here this child worked a long time to get the angle just right to land in this second ramp, but not overshoot it. Think about the experimentation and challenge of that. Here again are the Kodo Kids materials that comes with these nice wooden balls. And here what they're doing is trying to bridge a gap so that it jumps off this ramp and lands on the lower ramp. Again, this is something you can challenge children with after they've had lots of experience just messing around with materials like in that first photograph that I showed you. Here are sandbags that are used to support these materials. The ones in the pictures come from Kodo Kids, and you actually fill them with sand, and they're really heavy duty material. I tend to make a lot of my own stuff, so I use black tube socks. The white stuff gets pretty grubby after a while. I use black tube socks. And I tried filling them with sand, but sand filters through, and so everything gets gritty with the tube socks. I tried birdseed, but birdseed was too light. We're no longer using food for things like that, so rice and beans were out. What worked really well was filling tube socks with aquarium gravel. And it moved well, it was heavy and sturdy, and I used lots of different sizes of lost socks to create a bunch of different bags for this construction. The thing that's really valuable about having this material added to the ramps is children with limited motor skills can participate more successfully. They don't have to struggle with the ability to stack blocks neatly one on top of the other to make a stable platform. These sock bags, whatever you want to call them, are much more forgiving and allow children to interplay in a way that they might not be able to otherwise. Here are a couple of photographs from a Reggio classroom in St. Louis that I visited, and what I wanted to show here, they keep the cove molding in this basket, and they put a couple of bricks in the bottom so that it doesn't tip over. The other thing I want to point out is they have multiple links, which is really nice. But you want to start out with just the long ones, because if you start out with just the short ones, they will quickly become swords or lightsabers. And you really don't want that in your classroom. But if they learn how to use them with the longer links that they really can't use in that way, and then you gradually introduce the shorter links, you can avoid most of that problem. Here's another example of engineering in action. The children were testing which balls knocked over how many of these little metal people. They've got different weights and different sizes of balls. And the balls kept rolling away and missing the people. And so they created basically a cage to test that, to contain the whole thing. Another thing that I've seen teachers do if they're working on tabletops is use strips of manila folders to tape around the edges of the table that creates like a little rim that keeps things from rolling off the tables. A fixed ramp like this, where you've taped it to the table, allows for standard comparisons. I've seen kids test car after car after car to see which ones roll the farthest, which ones roll the straightest, which ones go the fastest. But then it's also fun to play around with changing the angle of the ramp. And children can, again, with practice and experience, learn how to do those sorts of things. It's also helpful to take things outside. So here are some young engineers working to make a structure that stays up, that's fun to play with. Using big materials like this outside, invite children to work together. It's with something that big and long, it's hard for one child to do that alone. The materials say, let's work together. And when you're outside, you don't have worries about everything getting knocked down. This was a group of mostly 3-year-olds that were building with these things. It was very simple. They could use tennis balls and have some real success. So this is vinyl fiberglass guttering. The other thing you can do when you're outside is it gives you the opportunity to work with heavy materials, big boards, rocks. The Early Childhood Center that I work with a lot has some boards that are 6 feet long and about 8 inches wide. They're really heavy. It's really hard for a child to move them by themselves, but with a couple of children working together, they can build balance beams to walk on, they can build ramps to roll things down. Sorry, here, the wrong button. When you have ramps outside, and you can then come up with all different kinds of materials to test. So here these children are predicting, and there's a big difference between predicting and guessing. The children, if this is their first time working with ramps and they have this collection of materials and they're going to see which ones roll and which ones slide, it's going to be a guess because they haven't worked with the materials enough to know what's likely to happen. But after they've spent a long time working with a lot of different kinds of materials, then it becomes a prediction that they can look at a new material they haven't worked with before and decide whether or not that's likely to roll down the ramp or slide down the ramp. Here's another kind of material that you can use for ramp ones. This is made with foam pipe insulation. It comes in a tube with a slit on the side. I cut them in half lengthwise and make these ramps that I typically use golf balls or wiffle balls that are golf ball size. You can also use pool noodles for this kind of thing. It comes in 4 and 6 foot lengths. And so it makes for a nice long piece for them to work with. So here it is in a classroom. This is a classroom of 3 and 4-year-olds. They're collaborating to create a long pathway. Their goal is to make something go across the room. And so both they and their parents can connect it to prior experiences with Hot Wheel racetracks or other kinds of roller coaster experiences. When you use this pipe insulation, you should use either painter's tape or masking tape. You'll be tempted to use duct tape, but that rips the foam pipe insulation. So voice of experience, learn from my tragedies. So they're having a discussion, and the kids there are saying, I think we need to start it higher. It wasn't making it all the way across the room. And so they're testing the angles. Then they're ready to test it. And see if it'll land in the target, a box that they have across the room. And yes, it did. I just didn't get a picture of it, sorry. But back to the journaling that I mentioned earlier, again, in this same classroom, they develop and use models to represent their ideas through approaches such as drawing. And so here a child drew this plan, wanted to do a loop with the pipe insulation, and with teacher support, was able to actually do it. Again, here's a commercial version of that same material from that same company, Kodo Kids. You can get 3 8-foot sections for $99. I'm sorry. It comes also with those wooden balls that it's heavier, it's somewhat easier to work with. It's quite a bit more expensive. So you just have to know what your budget is. Here's kind of an up close picture where you can see the pipe insulation a little bit better. And here I had a teacher who used zip ties and pegboard to make ramps here into a plastic bottle funnel and then down into the lower ramp to land in the target. Then here's a good starting place for some children, depending on where you are. This is a wire wine rack and a whole collection of different kinds of pipes. They've tried tennis balls, wiffle balls, Nerf balls, see how they would go through the tubes, listen to what kinds of sounds they made going through the tubes. So again, depending on the children that you're working with, this might be a good starting point for your group. Here's using PVC pipe. I've often been able to get donations of PVC pipe, but I can rarely get donations of the connectors. So I've most often had to buy the connectors myself, but can get scrap pieces of pipe. This is a material that it is important to sand the edges. They can get sharp edges if they're sawed, so you just need to sand the edges to make sure that the pipes don't have any sharp spots on them. And this is another way of doing PVC pipe on the wall. This is PVC pipe with magnets attached. This is a commercially available metal board that you can use magnetic objects on. You can also get what's called an oil drip tray. It's for changing, if you put under a car when you're changing oil, it's about that same size for $17, a lot cheaper than the thing with the wooden frame. You can also use a magnetic tape on the back of these or glue donut magnets, those round magnets with the hole in the middle on the back of these to use indoors or out. And then here's one of the cheaper ways. This is on the back of a bookshelf and it's the size of cereal boxes. It's free, you make do with what you have. And these make rolling pathways. It can roll here, down to this one, down to this one, down to this one, down to this one, and land down there. You can also do the same thing with paper tubes to get the ball to travel from tube to tube. Paper towel tubes. What's even better are the tubes that come with aluminum foil or plastic wrap. They're much heavier duty, stronger tubes. You can use them as whole tubes, or you can also cut them in half lengthwise so they're like the gutters and the children can then see what's going on more easily. and provide them with tape, and they can make lots of just tubes themselves. And most children will start out just taping tubes together to make a straight run. And so here, using painter's tape, the same kind of thing, just making it, and some of these are whole tubes, some of them are cut in half like gutters. Just other ways of assembling paper tubes. So again, communication is a big part of their investigations, documenting what they're doing, paying attention to what's happening. So I'm going to show you a study that was done in a 4-year-old classroom with the teachers I was working with down in Texas. The photos aren't all that great, but I think they convey the idea well. This is a teacher named Gail. She put this on the bulletin board outside her classroom to communicate to families and colleagues in the upper grades and administrators that important things were happening in her pre-K classroom. So first they made a ramp. And then they voted to choose 3 balls that they were going to use for the competition. So they had a range of balls, and children voted with connecting cubes to see which one was the winner of which 3 balls they were going to test. So then the question was, which of those 3 balls do they think will go farther? Again, these were predictions, not random guesses, as they were based on lots of experiences the children had had with rolling balls down ramps, just not these particular balls. So they had what they called the hairy ball, the lumpy ball, and the styrofoam snowman. Then they glued their pictures. So she had pictures cut the same size of all the children in the class, and they could glue their own picture on to make a bar graph so that they could see, starting with the baseline on the bottom and build up from there to see which they predicted. Then they tested them. So Michaela rolled the snowman ball she got from the morning assembly, and they put a piece of tape where the ball stopped so that it didn't interfere with the other balls rolling. Adriana rolled the pink stringy ball. And then I like this conclusion. Many of us were surprised. It was the smallest one of all that won. So again, to sort of sum up, engineering in preschool is exploring, do it again and again, collaborate, and share. So what we're going to do now in the next section is a lot of ideas across a range of classrooms to give you some suggestions for what you might do in your own classroom with your own children. I want to just briefly touch on balance and stability. We're not really going to go into that in this webinar, but it's something to explore. Exploring balance in their bodies first before they move on to more complex things. But here, balance in balancing the building materials that they're building. So this is a classroom of 4-year-olds in Austin, Texas. 20 children, 4 girls, 16 boys. You can just think about that. So they decided that they were looking at the effects of force and motion, the force on objects, and they were going to roll the cars and trucks. And so with pushing, there's their graph. You can take a photograph of it. You can use chalk to mark the spots. You could count how many steps to each car or truck. but very visually, they can see which one, at least on this trial, went the farthest. Here is squirting. So here are our little guys squirting in this way. Here's another little guy who has motor issues. And so this teacher was able to get him to squirt in a metal tray, which makes a nice noise. And he could be a part of making this and getting the exercise he needed in his hands, but then also participating in the squirting challenge, in a squirting challenge like this, using this kind of a squirt bottle. Here's a stomping. How can you make the biggest splash? Look at the ripples. Do they make curves or straight lines? Can you make a ripple with a straight line? Here is going out to see what they can do with kites, and not just once, but trying lots of things. Paper, plastic grocery bags, cloth streamers. Here they're blowing bubbles in the wind, talking about where they go. And I like this. Here's Cammie telling what it's like to blow bubbles in a 30-mile-an-hour wind. She learned really quickly which direction she should blow if she didn't want a mouthful of soap. Then once again, this is a 4-year-old classroom. Most of the Texas classrooms were 4-year-old children. But she's journaling about the windy bubbles. What did our bubbles do? So let's just take a moment, and in the chat, what are some things that you do to explore wind, to explore weather, to explore forces outside? Winter, things like making ice sun catchers, which would be really easy to do right now since it's 19 here. So in the chat, write down some of your ideas of things that you do. Musical scarves outside. Kites made from garbage bags. Bubbles on cold days. If you haven't tried bubbles on cold days, it's really kind of cool. They tend to rise because there's hot air inside the bubbles. If it's really, really cold, the bubble will actually freeze. That's probably a do at home with your own kids kind of thing. Humpty Dumpty eggs from different levels, paper kites, freezing water and balloons. I'm seeing here the suggestion of gathering materials, asking from Menards or other stores what for scraps. I like the comment too about water slimes, that paper cups filled with snow to bring into the classroom to build with, paper airplanes, freezing water in jars, how leaves move when it's windy, and can you move like the leaves? One of the things that I think is so important, not just budget-wise, but when you use things in your classroom that are just things like as a teacher and as a college professor, I just always kept a box in my kitchen, and I would just throw anything that I thought I could use recyclable stuff in there. So I always had stuff. I think it's important for families to know that those inexpensive throwaway things can really be used in meaningful ways. So lots of good ideas there. Okay, I want to talk about this a little bit. Sorry, talk about this just a little bit. I would suspect that most of you have done something with sink and float in your classroom. I want to propose a different idea called bobber and bottomer. And because sink and float, when the kid tosses something into a container of water, they have no idea whether it's going to sink and float. It's just a guess. But if they hold an object in their hand, put it in the container and take it all the way down to the bottom, so they've got it under their hand and they're holding it on the bottom of the container, then they can kind of feel that upward pressure of, is it going to float to the top or is it going to stay at the bottom? And so it becomes a prediction, not a guess. They're really using their own scientific observation of what that object is doing under their hand to determine whether it's going to stay on the bottom or bob to the top. So here they're checking out a bunch more. And the reason I have the potato here is I had a little boy who was really sorting back and forth. He had his bobbers, he had his bottomers. He was really on a roll, really knew what he was doing, was having a really good time with it. And then he got this potato. And if you have a really fresh potato that is really juicy, it won't sink to the bottom. It won't float on the top. It kind of hovers around in the middle. And he kept pushing it down to the bottom and it would come about halfway up. He'd push it down to the bottom, came about halfway up. And finally, he just set it over to the side and said, it's a potato, and went on with his other stuff. Here's a way to document their findings. You can either, this is a commercially prepared chart that allows children to actually put the real objects in those squares. You can also buy a shower curtain and use duct tape to make your own squares to graph with real objects. Just from a science perspective, it would be better to follow the science protocol, the math protocol of starting at the bottom and going up rather than starting at the top and working down. Here's another one of making boats. It's another way of using their own force. Assembling boats, one of many ways to make boats. And then how can we make them move without touching them? We can use the wind, we can blow on them to make them go. Here we did marble and rock painting. The children had had lots of experience with marble painting. And so we decided to add another variation, since they had been doing a bunch of things with rocks, to see if they could paint with rocks. And so they first practiced with no paint, just to see how the rocks moved and what they could do. Then they compared marbles and rocks. It's part of exploring how things move. And then we said, can you tell just by looking who used marbles and who used rocks? And of course, they could tell the difference in the kinds of lines that the rocks made and the marbles made. Every time I look at this picture, I just think about the white shirts. I'm sorry, here we go. Then we had them in their journal draw the rocks that they used, which works better, small or large. So even though, what's interesting, even though the large rock is really small and the small rock is really large, they actually were accurate representations of the rocks that he used. He just had a little problem with scale, but what the heck, he's 4. Then, and I was really impressed with this. This teacher had the kids do Venn diagrams. Again, they're 4-year-olds, and this was in the spring. But they really thought about the differences between, and this wasn't their first time using Venn diagrams, so what was the difference between a marble and a rock? And here's what they said, that the rocks move easy, they're smooth, they're straight, they're fast. The marbles, the rocks are hard to move, bumpy, jagged, but they all roll, they all had paint, and they all moved. So again, think about the language that's involved and the sharing that's involved in sharing their observations. So then, if we look at another performance descriptor, the effects of simple forces in nature, such as gravity, using a simple balance scale to determine which one is heavier. And this particular group of children really got interested in determining if they could make them even. They really kept trying to get it straight. This child got into, we wanted to do how many washers did the shell weigh, but then he also wanted to use the connecting cubes. And so he did one connecting cube for every washer he put in. So really pretty complex mathematical thinking. This one, he was pretty happy with it being pretty even. And I want you to just sort of look at the faces here of, this is serious, important work. I mean, they're really concentrating on what they're doing. I mean, they look like real scientists, don't they? Then I also want to talk just a little bit about the right tools. So if you go back to this picture, this kind of balance scale is pretty inexpensive, but it often ends up with catapult issues of children discover that they can put something on one side, slam down on the other side, and something flies across the classroom. But it's also a little bit harder for children to use. These bucket balances are a little bit more expensive, but they are easier for children to manipulate, and they can use both liquids and solids in it. Here, this is using the, do magnets work the same in water as they do without water? Children at this age don't really understand the properties of magnetism, but they can certainly sort into magnetic or non-magnetic objects. You can use just making piles like these kids did, or using the Venn diagram charts. Another way to explore magnetism is using magnetic objects on a paper plate and using a magnet wand underneath to move them around to magnet paint. You could also fill a 2-liter bottle with confetti, paper shredder, paper from the paper shredder, put magnetic objects in the 2-liter bottle, glue the lid on, and then use magnet wands to explore what they can find in the bottle. I want to talk about this. This is a typical activity that's used this time of year of making bird feeders using either peanut butter or shortening much more common now because of peanut allergies. But it can be a 20-minute do it, get it done activity, or it can be a thoughtful, rich learning experience. So if you want to make it that more thoughtful experience, you might imagine sitting with a group of kids and having them generate ideas. How can we get the shortening on the pine cones, and how can we get bird seed there? Try a couple of things. Choose their preferences. Some children might prefer spoons. For other children, a spoon is a cue to eat and is not a good idea. So you might start in the morning and say, let's think of some ways that we could get the shortening on the pine cone and the bird seed on the pine cone. And write down the ideas that the children come up with. And then later in the day, come back and say, here are the ideas we had this morning. Has anybody thought of anything else? And see if children can come up with some additional ideas. And then say, you know, this is something I think maybe our families might be able to help us with. Why don't you go home and talk to your family and see if anybody at home has ideas? And so spend, 1 or 2 days just kind of thinking of how we might be able to do this. And then actually start testing out some ideas. But I think one of the things that's most important in this process is help them understand that they're making choices, they're not choosing a winner. Because what is the right choice for one person might not be the right choice for another person. One child might really enjoy smearing the shortening on with their hands. Another child might really enjoy using a piping bag to, just like they pipe frosting on a cake, to pipe the shortening on the pine cone. Some children don't want to have their hands anywhere near the stuff. Other children just love to dig in. And helping the children understand that those are choices, and that what works best for one might not work best for another. So it changes something from a quick, fun activity to do into something that is much more thoughtful and rich and full of more learning opportunities. Really quickly, here are a couple there are a lot of good books on engineering and physical science that come out recently, and these are two that I particularly like. This one, it so happens, I was a professor at SIU Edwardsville for a long time. The husband of the author of this book was a graduate of our early childhood program. So that's kind of your little fun fact for the day. The most magnificent thing, the thing that I love about this book, is this little girl is trying to build the most magnificent thing and gets very frustrated. What this book shares is the value of taking a break to deal with frustration and just go away from it for a while, and then we'll come back to it. So in the chat, would any of you who have books that you especially like put the titles in the chat, because I think everybody is always looking for new books. Okay, we've got Newton to Curry, The Science Squirrels. Another thing that's really valuable about these books both is that failure is valued and failure is recognized as part of the process. Anybody else have book titles to share? If you think of any, type them in as we go. Those darn squirrels. So I'm going to add another thing to the chat request, and that is, I want you to think about what you're already doing and how you can make a space for more engineering. How do you connect to other disciplines? Stay away from the junkyard, great title. Maybe a tubes and tunnels investigation. What are investigations, topics that you've done that you've found to be particularly effective? And see the note from Karen that says to save the chat, click on the 3 dots at the top of the chat column and choose Save Chat. So I want to show you some other resources here. You're probably familiar with the Illinois Early Learning Tip Sheets. They have a number of things on physics, science, resources that I think are really worth you taking a look at. Here are some other ones from Illinois Early Learning. National Association for the Education of Young Children has some great resources on ramps and pathways. Community Playthings also has a lot of articles and sample activities of things to do for engineering and physical science. So if we come back to, oh, I like Boxatex. There's a whole world of constructing with cardboard and cardboard construction tools that is really fun if you haven't tried that. So if we go back to, looking at this and a reason for it in the larger world, if we want a vibrant business community with fullest possible employment in STEM and other good jobs, we want to support that from the very beginning. And that's not to say that the purpose of early childhood education by any means is job production. My purpose for supporting young children in early education is to create happy, healthy children. And that's personally for me, my number one priority. But if we can give them experiences that open doors, that that they can leave our programs being open to the possibilities because they've had experiences with science and mathematics and language and literacy that bring them to a broader world, then I think it's imperative for us to do that. So we want to set the stage with young children that they can do challenging things, that they can do hard things, that they can make mistakes and try again, that they can fail and have that be just fine. That's just part of the deal. I think that's the biggest gift of engineering to the world of early childhood education, is making failure an acceptable, respected thing, that rather than something to feel is something that you did wrong. So here we've got blocks and boxes and cars to count and sort, build big, beautiful cities with bridges. So all of those kinds of things bring children together in the challenging world that we're all in today. I just want to say thanks to the SIU Edwardsville Early Childhood Center. A lot of the pictures are from their classrooms and from my graduate students' classrooms. And then the teachers from Texas who shared their classrooms and opened their doors and tried all kinds of cool things with kids. That's all I have for this evening.